Thank you for coming. Um, I'm Rubens Lage. I've over 20 years working in the construction industry. This work is part of it was the paper generated at the end of my master's degrees, and conjunction with David Lamont. It's here, and it's just to give a quick overview. So I've seen like everyone, it's talking about data and it's talking about design and it's talking about design conception, but it's also everything is before the construction. So this workflow is during the construction and how we check if that design was built correctly and then if we need to make any change on this way. So I go to, so like the theoretical idea would be like that we have the design and then go build, and then at the end we hand over as built model. But we all know that it's not true because we have many disciplines and each one of them on site, they build on top of each other. So we start with the foundations, and if they are, let's say, 25 millimeters off, and then my column would be this 25 millimeters off. And if I don't check that, then the next stage, it's like I'm going to build a wall. Then this wall is going to be off, or then I have to like I just want to see. Will you see that? If let's say my breaker or then another trade say, hey, wait a minute, actually that dimension I have there in the model is not fit on site. Why? And that is already late. So and then the same with services. We have walls, and then you model a clash-free wall with all the OPs, and it's beautiful. But then when you get on site, actually they build those OPs a bit off position, and then your prefabrication pipes, they don't fit there. And then you just get to know when it's too late. So that's what this workflow is about. And it's not theoretical. It's something I've been doing last 2 years. The paper itself, it's analyzing this accuracy and speed of this workflow. So what we do to get our clash-free model. So we have the design, we check, review, go back, and then many different meetings. So the proposal here is we keep doing that, but during the construction phase. So how we do this, how we are doing that. So we go on site and measure what was built. And this study, we are using a laser scan. And it's a huge amount of data. I get there how to treat this data. And then check on site, measure the difference between the design and what was built. And then we go to the coordination meeting and say, so I built my wall, and then my trader said, guys, actually was built on site 10 millimeters off position. So, and then I bring the model to the coordination and see the other trade. The next trade is going to get this wall, say, no, it's okay. I'm going to change my design and issue a new review. Or then say, no, that's not okay. You go on site and you fix that. And then if once it, so that would be the first, let's say, change the designs, and then the information would go through construction, share, coordination meeting, and back to the design team. But if I say, no, that's not okay, so you go on site, you revise, and then we're going to check again and bring to the coordination meeting. And then if once it's okay, then we can proceed to the next stage. But it takes a lot of time to do that because you have to have someone with the latest scan and then bring this information to the model and then go to a coordination meeting, and the site is running, so everyone wants to get their job done. So how do we do it? Of course, this study could go in structural, MEP, architectural, but I could not do that. So it's the scope is structural and laser scan. There are other ways to capture reality capture, of course, but this study is just for using laser scan. And to process the data, it could be using like C#, Python, but I'm using something that's more accessible. It's Dynamo. It's an all Revit file, it's a native. So that's how it got these very long name. A critical analysis of speed and accuracy when updating structural as-built models with visual programming and point cloud survey data. So the research methodology was active research. So to diagnose on the situation, the workflow, and the literature review, then create an action plan and evaluate this plan, specify, and run again. So it was run a couple of times to get the results. The objective was, first one is do a literature review and say, okay, is it a new idea? Is there any paper around other material that is already talking about that? The second objective was really apply this technique, and then the third one is measure the difference in accuracy and speed. I'm here. Yeah, so those are papers used, and I would like to draw attention to the last line, because we have papers on data source using different data source, like can be total station, laser scan, papers on processing data using programming languages, Python, C#, and also visual programming, Python, Dynamo, Grasshopper. But I haven't found any paper that move elements to as-built position, because it's common practice in construction companies and whoever is doing as-built model, they get the laser scan and they get someone to draw a section and model the element, or there are some softwares that they get the point cloud and they model a new element. But that breaks your workflow. You have the design and you have all the information you built from the conceptual design to the construction, and then now you have a new model completely different, and the information is broken. And also takes much more time for you to model a new element than just get the design model and move the element to as-built position. So in terms just more to be more visual, so these are the workflows, many different options. See total station or laser scan as a data source, can be programming or visual programming. But just to summarize, those are the papers. So do you see the dark boxes? All the papers I found, they cover those areas. But then you see two light boxes, and they're not moving element to as-built position. And then I look on the market to see, okay, is there any software company doing this? I haven't found. If someone found, please contact me, because I haven't tried and haven't found that. And also another thing is the design, the level of detail. Because when you model a wall from the laser scan, and then you might, depending on the technique or processing technique you're using, you're gonna get all little bumps, and you won't get a parametric model. And that's no use for, like, you don't need that unless it's like something, a historical building, and then you want every single detail. But in the construction side, we only need the parametric element and the geometry to do our spatial coordination. And I'm saying spatial coordination is not the design one. It's doing the construction, because I'm assuming that there are some errors in the construction, and I want to spot that. So that's the proposed workflow. This is the workflow used on this study. So total scan, laser, point cloud, so laser scan, and the design model, because you're going to compare the design model against the laser scan using visual programming, it's Dynamo, and then move elements to as-built position. So we're going to have our result is a parametric model with the same level of detail as the design model. The only difference is we're going to add the as-built information to this model. So we will know if it's intolerance, out of tolerance, and then go from there. To validate the study, so first I measure the model without against the laser scan without moving elements, just to see how was the situation. Then I got the information from Verity. That's a software, it's a company, 3D Edge. So they do this, they perform those analysis. If you use Verity, you can get a report saying what walls and elements and floors, beams, whatever pipes, if they are in tolerance, out of tolerance, and then you get the geometry, the X, Y, and Z. That's the deviation. So I got this report for the same area, but then I run this script on this research, and got my results and compared them. So that's just the data source and the data processing. So was the data source, the laser scan was a P40. Like a P40 is a very precise laser scan equipment. And computer, it was Dynamo 2.1, and computer is not that big thing. It's just a i7, 16 gig RAM. And that's a script. Of course, it's huge, so I can't go through each point. But the main thing is I get the inputs. The inputs are the design model, laser scan, and your design, the tolerance for the project. In this case here was 25 millimeters. And then the script turns those point clouds into numbers, X, Y, and Z, and then measure each of those points to the design model. So they're going to get hundreds of points saying, oh, this one is 10 millimeters, this other one is 25, this other 11, 3. And then I get the median deviation. That's just a rough number. So I got all the numbers. Okay, well, give me only one number to tell me what's the position of this wall. And then the script move the element to the as-built position based on these on those numbers, and export Excel reports. And you can use for these Excel reports, you can use for progress tracking, and also you can get a number to your construction and say, okay, what's the accuracy of this project? What's the accuracy of this construction? And then you get it was 93%, 85%, and it's not a guess, it's a number based on the model. Okay, and the progress is the same. So that's just a quick one. So that's a script running. So we select the point cloud, then say what's the design tolerance, then select the element and run the script. You're going to see the right-hand side is the verification. If turns orange, it's because it's out of tolerance. If turns green, it's because it's in tolerance. You see down the bottom, it's 27 millimeters, so that's the deviation. And then the script moves, and you see it's 1 millimeter now. It's 1 millimeter because this dimension line is it's rounding the number. Run for the column and then run to the wall. It takes around 1 minute each time, so it could be improved. I can improve that because I'm selecting one by one, but there is a way to say I get a big area, so analyze all the elements at once. Just for demonstration, it's one each time. So that's the accuracy, and how measure this accuracy was. Remember I said all the points, so I measure all the points in relative, for example, this wall. So I measured before and said how many of them are in tolerance. And after I move, I measure them again and can say how many of them are in tolerance. The result, to be honest, was not good because was 39% the points they were in tolerance after moving using this the script, the Dynamo script. But the software reference that was Verity achieved 45%. So that gave me a clue that maybe this measure of tolerance is not the best one. The accuracy is not the best one. So I have another number that it's more promising. So you see the yellow part. Oh, sorry. The blue part in the chart is the deviation before moving elements. So you see it vary from like 0 to 2, 10, 16. And then the orange is when after moving elements to as build position. And the gray one is using variety numbers. So you see that was really good, was 93% and moved elements to the correct position. And we saw previously the script actually doing that. That's the average processing time. So it's around 1 minute. I don't have the number for Verity because Verity is a different process. As I said, like Verity gets all the elements and check them all at the same time. But in average, it's 1 minute. So I believe it's much better than get someone to link the point cloud in the model, draw sections, and then start doing. So for each one, it's 1 minute. So it's quite fast. That's just to summarize. In terms of accuracy, I believe might have a better way to measure accuracy. So it was 39%. But in terms of moving elements to as build position was 93, nearly 94%. So it's a very good number. Even in this study, I only analyzed one direction, so the perpendicular direction to the element. I believe in the future study, I could use X, Y, Z, and rotation, and align with, in conjunction with, what's it called? Artificial intelligence, and then get those numbers more like round and get better numbers out of that. So those are the references. I'd say the number 14 is Autodesk University class. It was very inspiring for me. And in this study, he shows how to check if you're concreting a floor, how to check that using Dynamo and using LaserScan at the same time they're building. They just finished, he checked, okay, it's okay, good to go, or revise. So I highly recommend that. So just to let you phrase, you can't improve what you don't measure. So I believe that it would be a huge improvement if you get more attention to the construction phase and measuring and come back to coordination. Thank you.